Hey, good morning, students. So we are going to do the last part of Lewis Structure Lab. Let me get to my notability. So we are now going to be going over the acetate ion, which is CH3, CO2, negative. So let's get started on step one, which is going to be finding how many valence electrons we have in this atom, or in this molecule. So looking at the atoms we have hydrogen, we have carbon, and we have oxygen. Okay. So the way I like to determine how many valence electrons I have is I like to use that periodic trend of looking at what column number you have. So 1, 2, 3, 4, 5, 6, 7. So this is the column if you did not have the d orbitals. And using this, I can determine how many valence electrons there are. So in hydrogen, since it's in column 1, it should be 1 valence electron. For carbon, it's going to be 4. And for oxygen, it's going to be 6 because it's in the 6th column. Okay, so let's come write this over here in my table. So electrons, 6, 1. Oh, I wrote that wrong. Carbon has 4. It's oxygen that has 6. Okay, there we go. Now, let's make sure that we also take into account our molecular formula when trying to find the total. Okay, so let's add those together. So for it's going to be 4 plus 1 plus 6. Okay, now to take into account these three, that means that there are 3 hydrogens with 1 valence electron. So we are going to times this by 3. And then for carbon, look, there are 2 of them. So we want to have 2 carbons with 4 valence electrons. So we're going to times this by 2. And for oxygen, there are also 2. So we're going to times that by 2 as well. I'm going to move this over so we can read that a little bit better. Okay, and now the last thing to take into account is this negative charge. And what a negative charge means in an atom or a molecule means that there is 1 extra electron compared to the neutral atom or molecule. So we're going to add 1 in here to be able to get our total valence electrons. So I'm going to times it out so that it makes it a little bit easier to add together. So if you times 2 and 4 together, it's going to give us 8, 1 and 3, 3, and 6 and 2, 12. Okay, and then I almost forgot that extra 1 over there. Okay, and then adding all this together, we're going to have 24. And this is our total valence electrons in the molecule. Okay. So step 2 is looking at connectivity. So this molecule is a little bit different than the other ones because since it is a carbon molecule, it gives a little bit more idea of what goes in the middle and what goes on the ends. So for this one, carbon is going to be attached to carbon, and this one's going to be attached to hydrogens, hydrogen, and this one over here is going to be attached to the 2 oxygens. Okay, and we know that because it's carbon here with 3 hydrogens, so that carbon has to have 3 hydrogens on it. And then this carbon has to be attached to 2 oxygens, so oxygen, oxygen, and then connect those 2 in the middle. And that was part of step 3 as well. So I'm going to put it right here. Now for step 3, I do also like to see how many electrons I used so that I can know how many I have left. So I have 1, 2, 3, 4, 5, 6 bonds, and each of those bonds has 2 electrons in it. So 6 times 2 is going to be our 12. So we have 12 electrons left. Okay. Next, we go to step 4. So in step 4, what we're going to do is we're going to be putting valence electrons, or sorry, not valence, lone pair electrons on the external atoms. And so we're going to be putting them on oxygen. And we don't have to, hydrogen doesn't need any lone pairs as it is stable with just 2 electrons. So we're going to put them on oxygen. So we're going to put 6 on each of them. We're going to put 6 on each because that will complete the octet for them. So as we can see, oxygen has one bond here, which is 2 electrons. So it's 2, 4, 6, 8 electrons around that oxygen. So that octet is full. And it's going to be the same over here. So it has that bond that has 2 electrons. We have a lone pair, lone pair, lone pair. So 3 lone pair of electrons. So it's going to be 8 in total. So we had 12 before this step. We used 12 to put onto those oxygens. So our electrons left over are going to be 0. Now we're going to look at the carbons and we're going to make sure that these ones also have their octets full. So on this one, this carbon, it has 1, 2, 3, 4 bonds, and each of those bonds has 2 electrons. So we know that this carbon has 8 electrons around it, thus fulfilling its octet. Now this carbon, however, has 1, 2, 3 bonds, so it only has 6 electrons around it. So we need to do something to be able to fix that. So one thing we can do is we can grab these electrons and move them down to make a double bond. And that is what we're going to do in step 5. Okay. Step 5 is looking at the molecule, seeing if we have full octets, and if not, making them into double bonds. Redraw this. However, on this one, what I'm going to do is I'm going to make a double bond here between the oxygen and carbon. Oops. Okay, we're going to draw in our lone pairs. And I draw them at an angle. You don't have to. You can draw them the way you drew them before. It's habit for me. Okay. So now we have lone pairs around them and a double bond there. So now let's see if this carbon has a full octet. So we have 2, 4, 6, 8 electrons around it. So this one has a full octet. Let's double check the oxygen, make sure that that one's good. So it has 2 bonds here. So each of those have 2 electrons. So that's 4 right here. This is going to be 6. This is going to make a total of 6 so far. And this will make a total of 8 electrons in that oxygen. So that one has a full octet, making that one stable. So this is going to be our final Lewis structure. Okay, and if we want to, we can also put these brackets on and put that negative charge here to make sure that we know that there's an extra electron in that molecule. So the next step is going to be finding the electronic geometry as well as the molecular geometry. So on this, what we're going to do is we are going to use this table that's from the procedure, and we need to look at how the number of electron sets around the molecule. So for this one, we're going to be looking at this carbon. So I'm going to put a star on it. That's the one that we're going to look for the electron geometry. And so we need to find how many electron sets there are. So we can tell that there's electrons here, and electrons here. So that's going to make 1, 2, 3 groups of electrons, or sets of electrons. And so our electronic geometry is going to be that trigonal planar. Now, for molecular geometry, what we need to find out is how many lone pairs there are around that atom. So looking at our molecule, looking at our carbon, we can see that there are no lone pairs here. So due to that, we're going to be looking at this one. So it is still a trigonal plane. Okay. And so the last step that we're going to do is we are going to be looking at this in a 3D model. And I'm going to do that using an app, which is called MolView. And so this one's really nice because it is free and you can look at any atom in a 3D form. Now, this is a lot more based off of organic chemistry, so they aren't going to use the exact Lewis structure we use. Instead, it's going to use a line structure, but we can still use it for us as well. So I'm going to put in all the molecules. We have 2 carbons, we have 3 hydrogens over here, and then we have an oxygen here and an oxygen here. And so I'm going to make the single bonds right here, the hydrogens to the carbon, and then the carbon to the carbon, one bond onto one oxygen, and two bonds onto the other. Now, I'm also going to put this negative charge on this oxygen so that we can get the right structure. So this looks like our Lewis dot structure. There is a carbon here with 3 hydrogens. And then over here we have a carbon bound to a carbon, bound to one oxygen with a single bond, and bond to another oxygen with a double bond. And so looking at this, we can see that on this carbon with the oxygens, it is very planar. The oxygens and the other carbon are always on the same plane. Whereas on this one, we can see that that would have the geometry of tetrahedral if we had looked at that one. So you can spin this around, look at it at different angles, and then that's going to be it for our acetate ion.